Well, welcome back, everyone. We're starting on this afternoon for the PAC-Bayes with Benjamin Guedj, who is from UCL here.
Yeah.
I think I'll just let you get straight to it.
Thank you. Thank you very much, Jan, Matthias, and Jeremiah. I'm delighted to be here. So thanks very much for the organization and also for putting us in one room. PAC-Bayes France has been quite dispersed for the past few years, and I think it's a very good initiative. I'm very conscious I'm standing just after lunch, so if some of you are fighting the urge to nap after what was a very good lunch, please refrain so. I'm going to be talking a little bit about PAC-Bayes, about generalization bounds. So I'll start by introducing what generalization bounds are actually in machine learning and why they are such an important feature of machine learning, in particular machine learning theory. And then I'll briefly introduce what PAC-Bayes is. But the core of the talk is really introducing this work I did last year with Fredrik Hellström. So Fredrik was my postdoc until very recently. He's now moved to Dublin, but I'll comment on this in a minute. So just to highlight why I think this falls very nicely actually into the PAC-Bayes addition, so to speak. So most of my research is really evolving at the crossroads of statistics and probability, which was the topic of my PhD. And since then, machine learning and optimization a little bit. So a very good tagline I'm using for a lot of time is mathematical foundations of machine learning. So I'm really standing on the theoretical side, I would say, of machine learning so far. And some of the keywords, so PAC-Bayes, as I've hinted, generalization bounds, of course. Also, more recently, in interest in mathematical analysis of deep learning. Over the past few years, I've also developed quite a lot of interest in information theory, and more broadly, machine learning at large. Why do I think this falls nicely within the PAC-Bayes framework? Is because PAC-Bayes, as we will hear during the talk, is all about understanding about the generalization abilities of predictors or hypotheses. I will use actually both terms quite interchangeably. So when you see hypothesis in here, you might hear me say predictors, just to make sure you guys are following. So essentially, you're drawing those, so those functional objects, from preserved distributions, which in some very few cases are actually proper Bayesian posteriors, but in many different cases, the vast majority actually not at all proper Bayesian posteriors, hence the PAC-Bayes connection. So this is Fredrik Hellström, and this is us enjoying sunny Valencia last year. This is a paper that we presented at AISTATS. Right, I'll start with the take-home message. The second message is that generalization bounds come in a number of flavors. If you have a variety of generalization bounds for which you can control the moment-generating functions of the loss, then the tightest bounds that you can obtain are obtained with some function that we'll describe, which is called the Cramér function, used as a comparator. So hopefully none of these actually make sense to most of you, which is why I'm not going to develop and highlight all those terms. That's like a message. But this really is a talk about what is the best way you can find the tightest generalization bounds for generic machine learning problems. So that's the outline. As I said, I'll cover a little bit what generalization machine learning actually is, and then I'll introduce the notion of comparators between generalization bounds. And then, of course, we're going to optimize for that comparator, and that leads to new PAC-Bayes bounds, which are tight in that particular sense. Right. I'll start by arguing that generalization is actually learning, most of it, really. So you probably are all familiar with this kind of picture. It's really learning 101. This one's taken from Wikipedia. But the main question we're asking is from some specific examples, from data points, what can you actually learn about some underlying phenomenon? In this particular case, you got this underlying phenomenon, which is the black solid curve, which is distinguishing between blue and red points. And the question you're asking is, based on collecting those data points, can I optimally actually determine that boundary between those two classes? And obviously, it might be tempting to use actually what we do with that green curve, which is essentially trying to sticking to every point, trying to draw a very complicated and sophisticated boundary, which is minimizing the error. But it's not very difficult to see that this actually leads to very poor performance. So if you memorize what you've already seen, if you stick to the actual training sets, you will usually overfit, and that's a bad thing in machine learning. So I like to think of generalization as the ability to not overfit, really, to really perform well on unseen data. Another thing which I think is interesting is that for the past decade or so, we've now entered the deep learning era, where most of the people outside of our community think that machine learning is literally deep learning, and that we all use deep learning and deep neural networks for everything. But I think those systems actually trigger a lot of very interesting questions in theory. In particular, there's a mismatch between what we know in statistical learning theory and the way deep neural networks actually operate. So most neural networks would be trained on some data sets to achieve actually a zero error. You would have a zero training error, essentially zero, when deploying actually your neural network. I think what's counterintuitive for a statistician like me is that this is a very good indication that probably they are overfitting. So you would expect those systems to actually have very poor performance when it comes to generalization. But actually, when you compute their errors on test sets, they're actually doing remarkably well. And so there's a whole stream of learning theory which is not interested in understanding actually why the systems are able to generalize whilst apparently violating most of what we know in statistical learning theory. There's this very nice paper from Misha Belkin and co-authors, where they conjecture that this is essentially what we knew. We've known this for a very long time, actually, in statistical learning theory. So if you think of H as a class of predictors, in this particular case, as the class of neural networks, complexity of H might refer to some measure of the complexity of the neural network. So proxy to that could be the number of layers or number of neurons. And then you have the risk, essentially the error you're making on your problem. The dashed line is the training risk. So as your system gets more and more complex, you're more and more likely to actually have a very low training error. But the actual one you're interested in is this one, the solid line. And that solid line is the test error. And after some time, it actually goes up again. Why is that? Well, exactly on the example I've shown just before, which is you're sticking so much to the initial data you've collected that you can't learn and you can't see what's happening beyond that data set. But Misha Belkin and his co-authors actually conjecture this might only be half of the picture. And this is what the other half might be like. So they conjecture that interpolation threshold, so we had before that sweet spot here, which is essentially what we're aiming for in machine learning. But actually, the more complex the system, it plateaus at some point and then it decreases again, entering what they conjecture to be the modern interpolating regime, so to speak. And what's interesting is that the error you achieve that regime is actually smaller than the error you had in the initial regime. Hence, a possible explanation of generalization for deep nets. So why does it matter in machine learning? Well, I'll start with some notation. Let's assume that we have, those are all very classical notations. So we assume we have a data set, which is an ID sample. I'll come back to the ID assumption later on. But we have an ID sample drawn from some unknown distribution, which I'll call D. And your data set consists of input and output pairs, right? So I'm considering completely supervised framework. But I'm happy to extend this to the unsupervised if you guys have some questions. We assume we have a loss. This is this small calligraphic L, and the loss is, for now, not bearing any assumption. We define the empirical error, just as usual, as the loss computed over the entire data sample, and the actual population error, L of H, which is the expectation with respect to the distribution of the data. So that's the expectation to be understood under calligraphic D, but I'm saving this for clarity. So those are the two main objects we deal with in machine learning, right? What we actually want to have is this, but obviously we can't compute that. So we use this as a proxy. And so most of the work that we do in theory is really about trying to control the discrepancy between those two terms. The first question we want to ask is for a certain hypothesis. So if I pick a specific H, if H is my favorite neural network, or if H is the empirical risk minimizer, or pretty much anything else, how can we certify that this particular hypothesis, with a good performance on the training data, hence a low empirical error, will have a similarly good performance on new unseen data. So trying to make sure this is small as well. So that's for a specific hypothesis. You could ask that question even more broadly and say, when those, a low training loss, imply a low population loss, uniformly over all predictors, over all hypotheses. All right? The typical approach is to bound what we call the generalization gap. So I'll define the generalization gap. For some hypothesis H, the population loss and the training loss defined as before, you let this gamma function be the generalization gap. That's simply the difference between those two terms. Okay? And the observation that motivates generalization theory is you're interested in L of H, so you write L of H as L of H plus and minus L hat of H, and reorganizing terms, you have that L of H, the population loss, is actually expressed as the empirical error plus the generalization gap. And so we're interested in upper bounds on the generalization gap, hence the name, generalization bounds. So this comes with a number of flavors. I'm going to comment on these briefly. First, it can be hypothesis dependent, or it can be hypothesis free. What I mean by that is that you could have a specific generalization bound, which is valid only for one specific hypothesis, one very specific algorithm. Or it could be valid for a very wide family of algorithms. This could be valid for all linear models with certain constraints of the parameters. Or this could be valid for just the ERM, which is maybe the one predictor you're interested in. And obviously, those actually pertain to different mathematical assumptions, but it's not difficult to see that the more constraints you put to a problem, actually the finer the bounds, obviously. So if you want very tight bounds, you will have to make assumptions. And the more it depends on the hypothesis and the class of hypothesis, and the tighter would be the bound. It can also be distribution dependent or distribution free. Distribution in the sense of the data generating distribution. This can be valid whatever the process that actually generates the data, or this could be valid under a certain number of assumptions, which are restrictive, possibly very restrictive on the data and on the model. Those bounds could come also in a number of flavors when it comes to its actual form. This could be expressed in expectation. So this L hat is actually a random variable. This depends on the distribution of the data. So you could take the expectation with that distribution and have a band which is expressed in expectation, so with complete certainty. Or you could have this with arbitrarily high probability, and this is what I'm going to cover now. So the PAC framework, probably approximately correct, can be traced back to this seminal paper from Les Italians in the 80s. Essentially, what we want to do is to bound the probability of making a big mistake. Okay, the probability of making a large error in that problem is bounded by some parameter that we call the confidence parameter, delta. And you can think of this as the probability of being misled by a training set. That's the maximal error you're able to tolerate on your particular problem, and that's inherited from the training set. Hence the high confidence statement, which is just the converse. So the probability of being approximately correct, I make this formal in an instant, is lower bounded by 1 minus delta, which is arbitrarily close to 1. So this is what it looks like with high probability in purple. I'm not quite sure the purple is easy to see, but with high probability, the generalization gap, which is that difference, L minus L hat, of some hypothesis H, is at most something you can control, and in many cases even compute, and that's this bound term. So you can think of this last term, which is the upper bound of the generalization gap, as some measure of complexity. Think about the KL, for example, in PAC-Bayes, but we'll get to this in a minute. So some complexity term, which pertains to the difficulty of your particular problem, times some term, which is log of 1 over the confidence, divided by square root of, this looks like an M, but it's actually an N. Just to make sure you guys are following. Keeping you in your feet at all times. And so it's easy to see that if you let this delta parameters be too small, this blows up. So you have in the end something which is the generalization gap is bounded by something which is super large with probability 1, which is true but not useful. So that's a trade-off. Right. So PAC-Bayes is really about blending PAC statements with a post-Bayesian spirit, so to speak, because you're not interested not just on a hypothesis, but you're interested on distributions of a hypothesis. So consider a number of distributions of a hypothesis. Let's say we have a reference distribution. I'll call it a prior, Q0. In many cases, not an actual Bayesian prior, but again, we'll get to that in a minute. And so you define actually the proper definitions of the empirical errors and the population loss with respect not just to a hypothesis, but to distributions. And so you just take the expectation with respect to some distribution Qn, and I'll call this the posterior, but again, it's not a proper valid Bayesian posterior in many cases, if not most cases. And this is just defined as the empirical error of the expectation with respect to the posterior of the loss. And the same for the actual population error. So you want to compare that sequence of posteriors to your reference measure, to the Q0 prior. And typically you would do this through the Kullback-Leibler divergence, which I recall here. Just to highlight maybe briefly the differences between Bayesian inference and PAC-Bayes. In Bayesian inference, there's a unique way up to constant, but there's a unique way to go from the prior to the posterior, and that's called the likelihood, right? The product of prior and likelihood gives you up to a constant the posterior, and that's uniquely determined. In PAC-Bayes, it's quite different. First of all, it's a model-free approach, so that means you can have a statistical model. Actually, in many cases, we do have one, but you don't need one. You don't need one per se to actually do PAC-Bayesian learning. And instead of a prior, we have any distribution, hopefully not depending on data. The posterior is something which possibly, well, actually, if it doesn't depend on data, it's not hard to see that it's not going to be very useful. But you want this to be, in some sense, consistent with the Bayesian update principle. So you want that some version of the loss times some reference measure gives you something which you want to call a posterior, but it's not actually a posterior. So in that sense, you have much less constraints. You're guided by the exact same Bayesian update principle. But you can pretty much pick anything. You don't need to worry about, for example, conjugacy or that kind of thing. So what makes PAC-Bayes a post-Bayes approach? Well, I'm just going to focus on the three important distributions that we have in this problem. First one being the prior, or the reference measure, as I called it in PAC-Bayes. You will see that most PAC-Bayesian bounds hold for actually any distribution for the Q0 measure. Whereas in Bayesian statistics, your prior obviously impacts a lot what you're doing. In particular, it impacts a lot the quality of your entrance. Same goes for the posterior. Most bounds will be valid for all distribution for the posteriors, whereas in Bayesian statistics, your posterior, as I said, is uniquely defined, so you can't just pick any. And same goes for the data generating distribution in Bayesian statistics. The modeling will impact a lot what you will be able to do, whereas in PAC-Bayes, this also usually holds for any distribution of data. So this opens very nicely to the possibility of obviously optimizing PAC-Bayesian statements with respect to one or more of those three distributions. This is one of the most famous PAC-Bayesian bounds. So this is the McAllister form. So the earliest references for PAC-Bayes actually go back to what were three very productive years at Colt at the end of the 90s by John Schoteler and Bob Williamson and David McAllister the following years. So this is the form of the McAllister bound for any prior Q0 and any confidence parameter between 0 and 1, but predominantly closer to 0. The probability that for any posterior distribution, the actual population error of that posterior is upper bounded by the empirical error of that posterior plus that complexity term I mentioned earlier, which in that case is a square root of the KL divided by how many points you have. All right. So this is really one of the most popular and pivotal bounds in PAC-Bayes. And from this, we can do actually a number of things. So from that bound, now putting this in more generic form with just this B of N delta and Qn, it depends on how many points you have, obviously, but also on the confidence parameter to that log of 1 over delta term and the posterior, obviously. So you can essentially do two things. You can compute the numerical value of the bound in some cases, not all of them, but you can compute it or at least approximate it. And that gives you very valuable insight actually on the actual numerical performance of your algorithm. But I'm slightly more excited about this second bullet, which is that you can use this as a completely principled way of deriving actually new algorithms. So you can try to find the posterior that is the argument of the infimum of this term. This becomes an optimization problem, which many different people have attacked through a number of techniques. So it could be Monte Carlo Markov chain algorithms, could be gradient descent or stochastic gradient descent. There's a number of papers of which the authors are in the room, actually, which are interested in variational inference and trying to find the optimal way to sample directly from that ideal posterior or optimal posterior, which is the one given by minimizing the generalization bounds. Just a quick remark as well on the variational definition of the KL, because this really is one of the cornerstones of obtaining those generalization bounds. And I think it's a very nice result, very nice and elegant results. And that's one you can prove in one slide. I'm not going to pass on that. This is due to parallel work from Shizar and Donskoy-Varadhan in the 70s. And the form I'm going to present is the one which is actually written a little bit by Olivier Catoni in its monograph in 2004. So the variational definition of the KL goes like this. And what's interesting is that this is a result which has been known in many different communities. I remember a heated discussion with Jeremiah, who was referring to other references than Donskoy, Shizar, and Varadhan, because this is actually a very well-known mathematical fact in many different communities. So here goes. This is the machine learning version of that result. So for any probability P on some measurable space and any function phi such that the first moment of exponential composed with phi is finite with respect to some distribution P, then the log of the integral of the exponential composed with phi is actually given by a supremum of this expression. So the integral of phi with respect to some distribution Q minus the KL between the reference measure P and Q. So this gives you a variational expression of this term, which is the one that actually appears in many generalization bands. Not only do we have the form of that supremum, but we also know about the distribution that achieves that supremum. If that distribution is upper bounded on the support, so it doesn't blow up, then the supremum is reached for a distribution which is very well known, not just in mathematics, but also in physics. And that's the Gibbs distribution. And that's given by the Radon-Nikodym derivative between the Gibbs and the reference measure P, and that's exponential composed with phi. So let's prove those two statements briefly. This is what we want to prove on the top, minus that zoom green thing. So you let Q be absolutely continuous with respect to P. And then you write minus the KL between Q and G, G being the Gibbs measure given on the top. You make P appear in this, then you use the fact that you can separate this to the log. You recognize the first term as minus KL of Q and P, and then still working through your way with the log and realizing that the KL is non-negative, so always positive or equal to 0. That function, which associates to Q minus KL of Q and G, actually reaches maximum in Q equals to G, okay? And that maximum is equal to 0. And then you get the results. So that proves both statements in just a few lines of mathematics. And the implication of that, the consequence of that result is this. If you pick phi to be minus some temperature, that was already mentioned this morning, if you take phi to be minus temperature times the empirical error, then that Gibbs measure, Q lambda, is actually given by the exponential of minus temperature times the empirical error times the prior. And you know from that result that it minimizes something like this, which is the empirical error plus KL divided by something. Looks familiar, right? So that really is one of the cornerstones of proving generalization. At this point in time, some of you might be wondering, why should you care about generalization? So let me try and convince you. Generalization bounds are both a safety check, theoretical obviously, but possibly numerical if you can compute the terms in the bounds. And that's an original training objective. So there's a number of formalisms. This can be done through straight concentration inequalities, having McDiarmid, that's a lot, or Rademacher complexities of VC dimensions. But more recently, I've been mostly interested in the last two, information-theoretic quantities and PAC-Bayes, and I'll actually only focus on this for the remainder of our talk. Right. That ends that very brief overview of generalization, in particular what PAC-Bayes is. So now we talk about comparators in generalization bounds. So if you recall, I started by saying we actually look at the difference between the population error and the empirical error. And most generalization bounds are actually about this quantity. That's simple, obviously, that's very easy to interpret, but it's not always tight. And by not always tight, what I really mean is it's almost never tight, right? That's not the actual proper way to look at the discrepancy between the empirical error and the population error. So the question is, can we do better? And that's really the motivation for this work. So first, we define the comparator function. The comparator function, I will call delta, and the comparator function is something that takes as input empirical errors and population losses, okay? So it's a positive number, and returns also a positive number. The only thing you assume is that this is a convex function. That's the only requirement. A convex function with two inputs actually is a comparator function. So what you want for this function is to compute to the best of your ability the discrepancy between the training and the population loss. So how do we do this? Let's start with the fundamental theorem that actually is used in this branch of optimizing for the best comparator between functions. So this is a very beautiful theorem due to Luc Béjean and co-authors, published at AISTATS in 2016. And so the only assumption, extra assumption that we make is that the loss is bounded. So without loss of generality, let's say it's bounded by 1. And for any comparator, so any delta, the probability that the discrepancy through the comparator between the empirical and population loss is bounded by the KL, as always, divided by number of points, plus log of an epsilon term, epsilon delta, divided by small delta, which is a confidence. And that epsilon term is given by this formula. So essentially what this means is that you can pick that delta function to be anything you want. It just needs to be convex. The price you will pay in the bounds will be through that log of epsilon delta. And so now the game is to actually make this term as small as possible. All right. A corollary to this result is that if you say that the empirical error is bounded by some constant, alpha, and the KL is bounded by some constant beta, and then you upper bound as well that complexity term, the epsilon delta, by some iota of n, then you rewrite the bounds as the probability that the actual population error of the posterior, which is the one thing you're interested in, is bounded by some quantity, b and delta, that I'll comment on. And this happens with a probability which is arbitrarily close to 1. That b and delta is expressed as the supremum over all rho, which is number between 0 and 1. So this is akin to the population error of the set of the comparator function applied to alpha and rho being bounded by this quantity. You're just replacing the different terms in the bound to actually find this expression. Why do we do this? Because it's useful to actually think of this kind of bounds as answering, given that the comparator between training and population loss is bounded, what is the largest population loss which is still compatible with the bound, right? And we go back to the previous one. So you're looking for the worst value of your population loss to still make this hold, okay? So it's a way of thinking about this kind of problem as delta being the worst operator that could actually act on your population error so that you still have a meaningful bound. As I said before, you can have a bound which is mathematically true, but in practice completely useless. If this is what you're interested in. This is trivially bounded by some number, right? If you think about the difference, you're looking at the difference of two numbers between 0 and 1, so it's obviously bounded. If you say that the probability of that difference being upper bounded by 10 to the power 30 is 1, again, very true, but very unhelpful. So what's interesting about that bound from Guedj and co-authors is that many existing bounds actually arise from this one. So if you think of the comparator, which is just difference, so the one that 99% of papers and literature are actually considering, you straightforwardly obtain McAllister's bound, which I shown earlier in the slides. If you're using what is called the Catonis family of comparators, so you index this with some parameter gamma, which is just a real number, and delta of gamma is given by gamma q minus log of 1 minus p plus pe to the gamma. So this is known as the Catonis family. You recover that bound, which is so the probability of the comparator between the empirical error and the population loss being upper bounded by a term which is very similar to this one, but you notice that we've removed the KL. We've removed, sorry, the square root. So we now have a much faster rate of convergence of that object with respect to the size of the sample. Another classical example is if you use as comparator the binary KL divergence. So if you look at the small KL, so if you guys are unfamiliar with this notation, the small KL is the regular KL between two Bernoulli distributions of parameters Q and P respectively. And this has a closed form. This is given by Q log Q over P plus 1 minus Q log of 1 minus Q over 1 over P. And this actually gives a bound which is very well known in the Bayesian literature, which is known as the Maurer-Langford-Seeger bound. And that bound tells you the probability of the small KL discrepancy between the empirical error and the population loss is bounded by a term which is very similar to the one we had with the Catoni family. So again, achieving a faster rate. So those are three examples actually of comparators which you might consider in this kind of bounds. And the question I'm asking is which comparator actually gives you the best bounds? So no, you want to optimize this with respect to delta. When the loss is bounded, the KL is the optimal comparator. That's a result which has been established by a very nice paper published by Fung and co-authors at NeurIPS 4 years ago. And that's up to a log term. So we know we can't beat that. But the question is, what about losses which are not bounded? So we do relax that boundedness assumption. Now I'll move on to trying to find the optimal comparator. So we'll first address bounds in expectation, not as probabilistic statements, but rather in uncertainty. So you let those losses to actually be the exact same as before with an additional expectation. You're taking the expectation with respect to H drawn from the posterior, but you also have the expectation with respect to the data generating distribution. And we define the CGF, the cumulant-generating function of any random variable, as log of the expectation of the exponential of t to that particular variable. So we use the CGF to characterize actually the boundedness, or rather lack of boundedness of random variables. So that's one of the first results we obtain. We call it the average case generalization bound. So with that, what's happening on this slide? First, we define a set of distributions. So we let P, that calligraphic P, to be the set of distributions such that all distributions are indexed by the mean. Okay, so calligraphic P is the set of distribution PR, where PR is a distribution where the mean is equal to R. You let C to be the set of proper convex and lower semi-continuous functions. So that's the set from which you're going to pick a comparator function. And you let F be the set of functions which satisfy this inequality. So what's happening here is that we want to control the discrepancy between the empirical error and the population loss by something which would be akin to the CGF of a particular distribution. So we want to use this as a characterization of exactly what's happening for the discrepancy between empirical and population loss. So for all comparators, we have that bound. which again should be reminiscent of what I've presented earlier, which is with a probability exactly 1, there's no result in expectation. The comparator, any comparator between the empirical and the population loss, and there's no upper bounded by the Kullback-Leibler or the product distribution between the posterior and the distribution of data exposed to n, because you have endpoints, plus log of new epsilon delta p, which is given by this. And that's essentially the worst case you're paying for the upper bound of the assumption we've made earlier. So what we mean with this result is that you can obtain a generalization bound which is valid for any comparator, and that obtains the faster rate we were interested in. Now we're going to particularize this bound. How am I doing with time? About 10 minutes, right? Okay, good. So how do we make this relevant beyond bounded losses? Recall that most of you are probably familiar with, for example, sub-Gaussian random variables. When you have a random variable which is sigma sub-Gaussian, so sub-Gaussian with a parameter sigma, this is characterized by saying there's a CGF that dominates your current variable, and that CGF is the one of a Gaussian distribution with variance sigma squared. You have very similar notions for sub-gamma, sub-exponential, and so on and so forth. So what we look at is the convex conjugate of functions. So the convex conjugate of f is given by f star, which is expressed as a function of y, as the sup over x of the inner product between x and y minus f evaluated in x. So we're using the convex conjugate to characterize what kind of CGF constraints we need. And to do this, we define this notion of sub-p losses. So what's a sub-p loss? You let P be the set of distributions such that, as before, you have a distribution whose first moment is actually R. And for all of those possible moments, what we do is establish the set of T as all the possible values of means of distribution that's miscible in that set. So you said that the loss is sub-pt if for any hypothesis and any t, you have that the expectation of the exponential of the loss times t is dominated by the expectation of some variable which is drawn from a distribution whose mean is the actual population loss of exponential times tx. And that's the class of sub-p losses. And that class is the class for which all the PAC-Bayesian theorems we derive is actually valid. So this is one of the main results from that paper, where we're looking both at the optimal comparator and also the bound which results from that optimal comparator. So if we assume that the loss is sub-pt, we define the Cramér function as the convex conjugate of the CGF, which is given by psi pt on the top. So the Cramér function is defined as the convex conjugate of that function. You define the bound functional just like we did before. So we're looking at all the different terms of the bounds, and we're looking for the worst case in the sense of the population loss. So we're looking for the population loss that still makes this bound valid, but which is the worst case. Then for any comparator, we have that bound, and that bound, so this particular one, but that bound is actually the smallest for the comparator, which is given by the Cramér function. So that establishes that the best way to compare the empirical and the population loss is through the use of that Cramér function. In other words, the optimal average generalization bound is obtained with this as a comparator. Now we turn our attention to a number of consequences of this, but maybe just first, let me state that there's a connection which we didn't foresee in the beginning. We use the Cramér function for mathematical reasons, but actually we realized that for independent and identically distributed random variables, the Cramér function appears in a number of works to actually characterize the probability of rare events. We weren't actually aware of that before starting this work with Fredrik. So the connection to generalization is somewhat natural in that sense. And that's something I think I'd be keen to maybe discuss and comment on, because that connection was not very clear to us at the beginning. So this paper from Cramér actually is the one which introduces a number of those notions. So it's really an absolutely impressive paper. But if you're interested in this kind of technicalities also on the Cramér function and the way it's used, in particular in probability and concentration inequalities, this book here is a classic, an absolute classic from Stéphane Boucheron, Gabriel Guedj, and Pascal Massat from 2013. There's a specific case, which is the one of the NEFs, the natural exponential families. If the set of distribution is a natural exponential family, then the Cramér function has a closed form. And it might be surprising, it's actually a Kullback-Leibler divergence. So if you're looking at distributions which are natural exponential families, then the Cramér function is given between Q and P. The Cramér function is given by the Kullback-Leibler between two distributions who have mean respectively Q and P. So in particular, if you use Gaussian distributions, if you know the variance of your distributions, then the optimal comparator is given by the Kullback-Leibler between two Gaussian with the same variance and different means. And that has a very simple expression that the square of the difference of the means divided by 2 times the variance. And we thought that having this kind of closed form was also particularly interesting and particularly elegant in the context of computing the bounds and using those as training objectives as well. So some examples of Cramér functions. If your loss is bounded, then the Cramér function is given as the small KL. It's exactly the same mathematical object. As I just showed, if you assume that your loss as a random variable has a sub-Gaussian behavior, then this is given by the square of the difference divided by the variance. We have similar notions for sub-Poisson and sub-Gamma distribution. The sub-Laplacian is a little bit more intricate, but we also have a closed form. So in the paper, what we demonstrate is that we have a variety of Cramér functions depending on the assumptions you make on the underlying loss and underlying data generating distribution, which make things completely explicit up to the point that you can, again, use those as very clear training objectives because all the terms in the bounds are explicit. Right. That leads to the last part of my talk, so remaining a few minutes. From those results, we derive bounds knowing probability. Remember, all the bounds I've just shown are in expectation. So we derive from this bounds in probability. So we assume the loss is sub P as before. And for any comparator, we show that with probability arbitrarily close to 1, we have uniformly over all posteriors that the discrepancy in the sense of the comparator between empirical and population loss is bounded by the term which features the right rate of convergence. We have that 1/n regime, which is the one we're more interested in. So that's the generic result for sub-P losses. And then we show, again, the near-optimality. I say near-optimality because that's still up to log factors. So the near-optimality of the Cramér comparator. So if you assume your loss is sub-PT, then you have this bound for any comparator. So that shows that the value of the bound is actually the smallest for the Cramér function picked as the comparator. And furthermore, if you let this epsilon term to be the one defined by the Cramér function, then you have with probability 1 minus delta at least that the population loss is bounded by the value of the bounds evaluated in the Cramér function with the epsilon term that corresponds to that Cramér function. The last bit of that result tells you that if you define the comparator to be something indexed by some parameter t, to be tq minus the CGF, then we have this flavor of the PAC-Bayesian bound, and all 3 different flavors have interests, in particular when it comes to numerical computation. But the gist of all 3 is that we show successfully that the Cramér comparator gives the smallest possible bounds, right, up to that log factor. The second inequality tells you that you have valid PAC-Bayesian bounds when you use this comparator induced by the Cramér function. And the third one gives you a parametric form when you fix t, so that you can use this bound more efficiently to train directly your algorithms. So again, using this right-hand side of the bound as a training objective. We have a number of other results in the paper, but I'm reaching the end of the talk. So the main takeaways really is that generalization bounds are important in machine learning. And the way we actually compare the terms of the generalization gaps make a lot of sense. It's quite important. We're not tied to using actually only the difference and the introduction of this notion of comparator, which predates by a number of years of work, is really key in understanding how those objects and those bounds actually behave. The optimal choice for the comparator function, the main takeaway is that this is the Cramér function derived from the CGF that you use to control the data generating distribution. And last but not least, when you have a natural exponential family, this is equivalent to using the KL divergence to compare the empirical error and population loss. That leads to a few open questions, which I'm very happy to discuss now and also beyond during those 2 days, if you guys are interested. The first one is, can we extend beyond CGF controlled losses? Are there any extensions that we could consider that doesn't reduce to upper bounding the CGF of the existing data generating distribution with some distributions that we know and control? Obviously, you would like to get rid of that log term, that extra log term, but we don't have a good roadmap to actually do that. Another question is, does this strategy apply to heavy tail losses? There's actually quite a number of PAC-Bayesian generalization bounds applied to heavy tail losses, but they're mostly valid for looking at difference between the empirical error and the population loss. So one direct consequence of our current work is trying to adapt the exact same methodology and extend the proofs to the KL heavy tail losses as well, and see what this means in terms of the CGF. I mentioned earlier the connection to information theory. One idea we had also with Fredrik was to derive conditional neutral information bounds directly from this kind of bounds. And last but not least, how do you, in practice, calibrate this conditional CGFs in practice, and how do you use this in actually optimizing the bounds? So that's the paper, with the QR code leading to the paper. I thought I'd close by also mentioning, if you're interested in this kind of things, that's Fredrik and I, along with Giuseppe Durizi from Chalmers University in Sweden and Max Radziński from University of Illinois in the US, we wrote that book called Generalization Bounds, Everything You've Always Wanted to Know About Generalization Theory. That was the working title. And that's been published earlier this year in January in the Foundation and Friends of Machine Learning collection. And with this, I'll stop. Thank you.
Good. Thank you so much. Do we have any questions for Benjamin? Yes.
For example, data chain losses. I think perhaps you have already saying before that you are also doing additional methods to something that actually once optimizing a bound that is not the tightest.
Which is
so when you said something like in the first part of the talk that you're exploring the existing methods to sample from the exterior, defined directly from university.
Yeah.
Something like this method might work. Anything losses, or they being designed so far?
Let me make sure I understand your question. You're saying in many different bounds, we can use optimization techniques or sampling techniques to actually directly sample from the surface area or compute the bounds, right? And the question is, does this still apply if we have a heavy tail loss? So there are two different questions. Can we do something? The answer is yes. Does it work? The answer is maybe not so primitive, I would say. So in particular, when it comes to sampling, so I mentioned this in this form of bounds. Yeah, there. So we might be tempted to use sampling to actually generate that Q star, okay, which is the optimal posterior. The problem is you possibly will be sampling in very high dimensions. So there's a computational bottleneck that arises pretty quickly, which is why actually version inference techniques have been a bit more successful in directly optimizing from this band. In the case of a habitat loss, you would probably not find the influence in that bound term, right? That will only pertain to computing the empirical error. I don't really see any difficulty in doing this. The only thing to think of is really in practice, this being very slow or taking up a lot of memory. But I'm not quite sure if this answers your question. Does it? Does it? Okay. 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 Thanks. Yeah.
Maybe this is a bit of a basic question, but within this PAC-Bayes framework, how would you actually perform a prediction? Because the concept of a likelihood doesn't really seem to exist, right?
Yeah.
Because usually, if you let's say you found the optimal posterior in like a Bayesian context, you would integrate the likelihood of posterior to make a prediction. But in the PAC-Bayes context, you don't have a likelihood. So in the risk, it actually seems like you randomly draw something from your posterior because you do lost expectation. But why would that actually be a good strategy? Like it wouldn't make sense in practice to do that, right?
So, I mean, you're perfectly right. First thing that comes to mind, once you have very good posterior, so let's say I have this optimal posterior on the slide, yeah? The first thing you could do is actually sample directly from it. But that would mean having a different hypothesis every time. Every time you put a coin to your machine, you get a different predictor, right? Which a theoretician is not so much of an issue, but if you talk to someone from industry, they would scream in horror, right? I mean, obviously you don't want that.
Just running SGD once, it's also stochastic.
So it's also stochastic, that's right. But the point is, you will pay essentially the variance of that optimal posterior, right? So rather, you can look at the expectation of this. So look at the expectation of H, where H is drawn from this. You can look to pretty much any relevant moment of this posterior to actually create a more stable version of the hypothesis generating.
And if you want to calculate the mean, what would be the measure on the posterior space to get that mean?
You want to calculate the what, right?
If you want to calculate the expectation, like the mean posterior, basically, right?
Yeah. Yeah.
What would be the measure you would be using? What
do you mean by measure?
How do you average posteriors?
Well,
and how do you average?
You're averaging hypothesis, right?
Absolutely.
So this H is the expectation of H dq H, right? So you're averaging hypothesis with respect to the posterior.
Right.
Yeah.
It's a little bit confused.
If you think about those hypotheses as, for example, being indexed by parameters, let's say those are neural networks with 5 layers.
Hypotheses are functions, right? So yeah, you would average with parameters.
I mean, if you consider a parametric hypothesis, it's the exact same formula as if you have non-parametric hypothesis. In the case of parametric hypothesis, if I have neural networks, you can integrate over the weights of neural networks.
So you would just use the effect measure on the weights.
If you have neural networks, yeah, that would boil down to essentially that.
So then it would depend on the parameterization what you mean. So it's not. I just wonder how it is well defined. The mean of a hypothesis.
I mean, it's exactly defined like this. You can always compute. You can always write that expectation. Computing it, of course, is a different issue, right?
Yeah, but there isn't really a canonical measure of parameter space. But yes, that's on top.
Okay, maybe we can take this offline after that.
Yeah.
You presented the double descent curve early on, and it's always something that I found kind of hard to make sense of, because I don't feel like people are measuring the complexity correctly. But that's another conversation. How can I use what you presented, or just the general PAC-Bayes framework on generalization bounds to think about this curve? Like, could I take your L hat at H and your generalization bound and then plot it as a function of this complexity of H and see if it has the same behavior? And if it doesn't, does that mean it's not working well?
So that's a good strategy, but that's again provided that you have a very good idea what complexity is. I think this is much more conceptual than plotting actual quantities, because complexity of H can be widely different depending on the problem you're looking at. But I think that's essentially it, right? What has been conjectured and checked on some experiments, in particular in deep learning, is that the empirical and population error actually reach lower levels after some point, right? And that conjecture of the plateau is something that is really directly narrated from this paper. I don't think we have yet a good theoretical understanding of what's happening, right? When this was published, this was all but a conjecture. Right? Does that answer your question?
If I take your PAC-Bayes bound,
Yeah.
can I recreate this curve? Like, would it have the same?
So it depends on how tight the bound is. If you have a bound, which is, as I said, 10 to the power 30 is a valid bound, right? But that can show at all this kind of behavior. So you need to have a band which is tight enough so that it actually recreates and exactly mimics this kind of behavior.
More like a comment following up to the question about optimization. So we spent some time in this direction. Basically, you do it via Hellström gradient approach. So you have this variation problem, and then you could write something like gradient percent on the space of measures. If the space of measures that you're interested in has finite second moments, then you can do this. And then you can actually tackle things that look fairly non-standard, including posteriors that have no known form. So you couldn't write down the density, but you can actually compute the posterior, which is kind of interesting. But the computational issues you run into is that it becomes an adaptive particle system. So now, for that to converge to anything meaningfully, you need to actually have the number of particles that you run at the same time go to infinity as well as the length of the chain. So if you compare that with standard MCMC, we consider that to be computationally difficult. And then we basically trace one particle over time. Now imagine we have 100 particles and they all interact with one another. So that's kind of difficult. But I think that there are some reasons why that's actually a very exciting way forward. But I concur that it's not practically feasible at this moment in time. But if you're interested in small scale problems, I think this can already do something interesting. I can send you the paper.
We talked about what it means in small scale thing, because
Yeah. We give sorry, probably makes sense to take that offline. I just wanted to inject my opinions.
We'll
Anyways.
about that tomorrow as well.
Just to say as well, you won the argument because I now refer to this result as Dom's covariant theorem in my publications. So.
Only took me 5 years, right?
Well, I think that's all the time we have, but thank you very much.
Thanks.
For